I decided to try not moving the podium and doing the class from over here. It'd be a little bit different today. Does that work for everybody? Too bad if it doesn't, because we're already set up to go. But so everybody that's used to pointing towards the center of the room, you can swivel your chair or point this way. So what did we end with yesterday? And this is one of those moments where I'm testing you. I actually know the answer to this question. Did I tell you about the class where I got really bad performance reviews from the students because I decided to show off? I walked into every lecture, into the lecture hall, and I started every class with, what are we talking about today? And I wouldn't start the lecture until somebody in the class could tell me what today's topic was. Now, I always knew what it was coming in, but I don't think the class knew that I knew what it was, because then I did all the lectures just writing on the whiteboard and stuff. I didn't use any PowerPoints the entire term. I thought that that was like showing off. I was like, this guy knows the material so well, he doesn't even need slides. Yeah, the students didn't think so. The students thought that I was unprepared and didn't know what the class was about. So I try not to do that. So when I ask you guys, what's today's class about? Or what did we end with yesterday? It's not because I forgot. Probably. It's because I'm trying to see if anybody wants to interact. Because for me, class is way more fun when you guys talk to me. It's way boring when I just talk at you. So anyway, what did we end up with yesterday? Anybody remember? Yeah. We were talking about the things that impacted the power that it took to create the chips, right? Or I mean, I often will switch between talking about power and talking about force very quickly. And why is that? Somebody remember why I will switch between power and force, especially when I'm talking about, because they're not the same thing. They don't have the same units, right? They're totally different things. But the units for power and the units for force are related, right? So why do we make that switch often? Why do I make that switch? I don't say we. You don't have to. Yeah.
It's hard to measure force, but it's easy to measure power.
It's certainly more expensive to measure the forces. If we wanted to measure, if we've got our part here. Let me see. Try to get this, if I can remember the buttons. Yeah, sweet. So if we want to measure the force that's happening right here at the interface between the chip and the tool, so the force that's happening right there along that edge where the tool is moving through the workpiece material. Wish we had one of those fancy 3D printers when we made this that had like 2 different color filaments. So I could have made, or 3 different colors would have been cool. I could have the tool be one color, the chip be a color, and the workpiece be a color. I have yellow though. I suppose I could paint it. Right? I get some like model airplane paint. Right, but you say it's hard to, don't let me get too distracted either. It's Max, right? Don't let me, so today I think if I can see it, that's what's on the screen share, because I'm sharing the desktop, I think. But if you're at home and you're typing comments, I can't see those. So sorry. I'll review them later. Maybe. It's hard to measure the force, right? Because how would we measure this force? If we want to know, so we often talk about the force that the chip puts on the tool, or the force that the tool puts on the chip or on the workpiece. You could say either one, right? Because there's that interaction between the tool and the chip. And so that chip actually slides along the edge of the tool. So if we wanted to measure that force directly, what would we have to do? I'll give you a hint also. That force has got like, what's the word? Like unit vectors in all the directions, right? It's a 3-dimensional vector for that force. So it's not lined up with the X or the Y or anything directly. So what would we do if we wanted to? It is possible. I have done direct measurements of cutting force. So we can do this, but what do we have to do if we want to do it? How do we measure force in general? Anybody measure force today? I measured force today. Every morning, after I take a shower, before I get dressed, I measure force by standing on a scale and having it read a number. Well, actually, Bluetooth's to my phone. But, right, we're measuring force then. We're measuring the force of gravity pushing me down. I try to do it in the morning because you weigh the least in the morning. You know that? Yeah. I can swing 5 pounds at night. If I measure before I go to bed, measure in the morning, I can swing 5 pounds. So how do we measure force? I just gave you an example. How else do we measure force? Any other ways? Yeah. So if we could measure pressure, we could divide by the area, right? Pressure equals force times area. Yeah, so we could divide by the area, we could get force back. How do we measure pressure though? Yeah, I think we said it right. Yeah, whatever. This is a relationship because pressure equals force times area, right? Or force over area. Sorry. I have to write it down. I can't do these things out loud on my head. If we had a whiteboard, I guess we do. So what would we do if we wanted to measure the force of the chip on the tool? Because as this workpiece is spinning around, assuming that the tool isn't also spinning around, there's going to be a force between the workpiece and the tool, right? There's a force that's pushing the tool away, right? The tool's trying to go that way. If this is pushing down on it, right? Imagine you take a jar of tomato sauce and you put it on the countertop, and then you open the lid. I don't recommend this, by the way. Don't try this at home. Train professionals. But you open the lid. There's a vector of, if you had something that was stopping your thumb as it was going around, it would be pushing down on that, right? So if you ran into something. So how do we measure that force? If I wanted to measure the force directly in the machine tool, what would I do? Yeah. So we can measure the power very easily. But we had to do all that experiment to get all those factors, right? In order to actually get those factors, we had to measure force at some point. And so to do that, we actually take like a industrial version of like a bathroom scale. And so I wouldn't mount, you're not going to fit it in between the chip. You're not going to fit it in between the chip and the tool. But if we held the tool rigidly in something that was attached to our force sensor, then when we apply a force to the tool, that rigidness will transmit the force through to our force sensor, right? So we could put a force sensor in our lathe. We could often in the mill, we put the force sensor holding the part, and then whatever force, as long as it's not accelerating, whatever force is pushing on the part to try to move it is also pushing back on the tool, right? Unless it's accelerating. How do you know if it's accelerating? It flies across the room or the machine tool. That was fun, but I'm going to need that pen. I thought it was safe too, because it was pretty far away before there was a person. All right, so as long as it's not accelerating, we know that whatever force is pushing on the workpiece is pushing on the tool. Whatever force is pushing on or whatever force the tool is using against the workpiece. Okay, so we can measure force, but what's your name again? Andrew says it's way cheaper to measure power. Andrew's correct. It's way cheaper to measure the power. And we know the relationship between power and force is power equals force times velocity. So we can get the force. What is that force, though, that we get? So if power equals force times velocity, let's draw our picture. What orientation should we draw the picture? So here's what we have in our little model there. Right, and we've got a tool here, and the workpiece is rotating this way, so that's like drawing this on the piece of paper, right? And the chip forms here, and it goes that way and comes off as we feed the tool. So there's a tool, and it feeds in that direction. And this is the speed, right? That's the rotation of the workpiece. So the force we're talking about is the force that this chip here, this being created, is exerting on the tool. So it's the force the chip is exerting on the tool. It's equal, as long as it's not accelerating, to the force the tool is exerting on the chip. Does that make sense? All right, so if we go from this view, I'm trying to channel my daughter's art class. They were learning how to draw eyeballs. Let's see if I got it. So I got an eyeball here. And I guess need some eyelashes too. And we look straight down the cutting edge of the tool. So we're going to look straight down the cutting edge of the tool with our eyeball. So that would be, if I was in the machine, it would be like I was doing this, looking straight down the edge of the tool. And then, with the magic of art, we zoom in. We've got our tool. We've got our workpiece. And we've got our chip. And then we've got some interface between the chip and the workpiece. So over here, it's workpiece. Over here, it's chip. And so somewhere in here, it used to be workpiece and then it becomes chip all of a sudden, right? So there's a transition, and that's going to happen in this model here. Focus, focus, focus. It was right along this spot here. So anything over here is workpiece. Anything over here is chip. We got that? All right. And then if we project this plane, so this is the new surface that was made. We project that out. We could actually measure this distance here. We call that T1 for thickness 1. T1 is the uncut chip thickness. So that's the material that we have not yet removed, but we're about to as soon as the tool gets there, or as soon as it gets to the tool. And then we've got this here, T2. T2 is the chip thickness. That makes sense. So we've got T1 and T2. So how do we know what T2 is? We pick the chips up out of the bottom of the machine. We can pick the chips up out of the bottom of the machine and we can measure what the chip thickness was. So we can, because remember we looked at that zoomed in video, we saw that it was like squishing the grains of the material and changing their orientation relative to each other. So T2 will not equal T1. You'd think it should, but we've mushed the material. It's like when you take your peanut butter and jelly sandwich and you squish it. It's still got the same volume of peanut butter and jelly, but now it's like a pancake instead of a sandwich, right? So we squish that chip. We change the shape of the chip, so we can measure that chip thickness. We can. How do we know what T1 is? I mean, we could try to zoom in and measure it as it's going by, right? If we had a high-speed camera picture of this, we could probably estimate what it was by measuring. But don't we choose T1 as a process variable? That's one of those PVs, one of those things that we get to choose is T1. So what is it? So what are the process variables we talked about, CNC machining? We did this last Thursday. We made a list of process variables. We talked about them. I think one of them was like, what machine tool are you using? You would think it was related to depth of cut. And we often, when we look at this model, it's often referred to as depth of cut. But in our vision of this, right, our depth of cut is how far in and out we're going like this. So when we talk about depth of cut in a turning operation, if we're doing an OD turning operation, our depth of cut is this distance. It's how far into the material did we plunge, which in our picture here then is in and out of the board. So our depth of cut will control the width of the chip, but not the thickness. And the width of the chip is the same for T2 and for T1. Should be the same. So it's not the depth of cut. So what lines up with this direction? Because it's the motion of the tool in that direction. So is it, yeah? So if we go back to this picture, so our feed in that direction, if we express the feed in distance, the distance per revolution, I didn't want to use capital D because then we would have thought I meant diameter, right? So lowercase d. I just had to remember if it was B or D. Anybody ever have those moments? Little lapse of dyslexia, maybe? I don't know. So D, distance per revolution. So in the English system, what distance do we use? In our Americans, it's not really even the English system. They use metric over there. In our American system, what units should we use for that? So we're going to use inches per revolution, right? And so I said that feed in inches per revolution is like the distance between these two ridges as we go across the part, right? Okay, so inches per revolution. And we're looking for, what unit are we looking at? Wrong direction. So we're looking for inches. So that's pretty close. But also, if we look at this, so our thickness, so our feed is this direction, right? But our thickness is this direction. So those two dimensions are related, right? So it's actually the feed times the cosine of this angle here, which is the side edge cutting angle. So cosine times, so feed times cosine of the side edge cutting angle gives us our uncut chip thickness. So if the side edge cutting angle is 0, like in this dimension, what's the uncut chip thickness? So here our side edge cutting angle would be if I turned the tool either this way or this way. But right now, where the tool is interfacing goes straight into the part. It points right at the center of the part. So if the side edge cutting angle is 0, what's the uncut chip thickness? It's equal to the feed, right? And I suppose if the side edge cutting angle is 90, then the uncut chip thickness is what? Infinity? Or right? So you can't go all the way to 90. All right, so that's that side edge cutting angle, that's this angle this way on the part. We got another angle here. What's that angle? If we look here, that angle is, I wish these were more than one piece. Imagine, if you will, we have this fancy high-tech black tool. And we're going to do our cutting operation. So here, that angle would be 0. I could tip the tool like that. So here, the angle is 0. If I tip the tool like that, it's positive. If I tip the tool like this, it's negative. So this orientation of the tool is showing up here. So here, and we call that the rake angle. So alpha is the rake angle. Why do we care about that rake angle? I mean, one, it's one of the settings that we get to set, right? It's a process variable we get to choose. So why do you think we care about the rake angle? Why would we change the rake angle? Why not just always leave it the same? Anybody? Yeah. So it may impact tool wear. That's not really the primary thing that we're worried about. What's the focus of today's lecture? We never did answer that question this morning. Yep. So power of cutting and force and chip formation. So power, force, and chip formation. So, and remind me again why we even care about the power and the force and all that stuff. Yeah. Because we don't want to break the tool. Also, so tools are pretty strong these days. So the other thing that could happen is we could create a cut that takes more power than the motor on the machine tool has can possibly generate. And has anybody been in the lab and heard the tool go into the workpiece material and then you could hear it slow down? You hear that, like, especially the mini mills. You hear them, they get that, they go, ee, and then it starts cutting. It is, ee. Anybody ever heard that as the tool goes through the material? So when it sounds like it slows down, that's because it slowed down. Because we were using more power at the cut than the motor was able to generate. If it slows down too much, it stops. It's in motor jargon, you could stall the motor. So if you, who's ever like a little toy car or whatever, and you spin it up and you hold the wheel and it doesn't turn, something like that, or like a skateboard or whatever. We've all seen this. We've all stalled a motor before as we were growing up and getting exposed to these things. As you do with a vacuum cleaner, right? You get too much like yarn or whatever wrapped around it and the thing stops and it's still trying. It's fighting, but it's not going anywhere. You stalled the motor or you stalled the system. So yeah, you can do that in a machine tool also. You can also destroy the motor. That's more expensive than destroying the tool, in my thankfully mostly limited experience. We've only replaced a couple motors on machine tools. All right, so we care about it for, if the force is too much, then the power is going to be too much, right? If the force is too much, the tool's going to break. If the power is too much, the motor can't generate it. So we care about it for those reasons. So if we're doing experiments, what are we trying to do often then is reduce the cutting force that it takes, because we know that reducing the cutting force will reduce the power required. So we may change the rake angle to change the cutting force. Now, what were the factors we said yesterday go into how much power it takes to do the cut? Remember the factors with an equation we looked at? Yep. So specific power. There was a feed factor. I think we called that C. We called that Q. This is material removal, right? So there's a tool wear factor, which we call W. So the feed. And this is the specific energy for cutting. And so this, like this times this times this, is the power of the cut. Now, the power that we measure easily in the machine tool is the power of the motor, right? So we need to add in this efficiency factor if we're measuring power at the motor. If we're just talking about power at the chip tool interface, we ignore that, but it's not the thing that we read on the spindle motor. Okay, so that's our power. All right, so that's our power. So we'd like the power to go down. So we can, but I said if we adjust the rake angle, if we adjust that rake angle, we can change the power. But where's the rake angle in this? Because I told you if we change the rake angle, we can change how much force it is. And if we do that without changing the velocity, then we've changed the power, right? I didn't say we had to change the velocity, just the rake angle. So how does that impact how much force it takes, how much power it takes? Let's look again at, let's start again. Our tool, our workpiece, our chip, workpiece. So I said in this area here is where the workpiece becomes chip. So if we change this angle, if we do another one, where it's like that, would you be willing to believe that it might change that angle too? In fact, if we observe it happening, we see that it does that. So what are the physics here of the chip tool interface? So I've got my tool and I've got my chip. I'll go ahead and draw in the workpiece here, but we're gonna really focus on the interface of the chip and the tool. So what direction is the chip going? So if we assume that the tool is stationary, right, because it's just relative motion we're talking about. But if we assume that the tool is stationary, the workpiece is moving this way. Which direction is the chip going? It's flowing along the edge of the tool, right? The chip's going that way. And so what's happening as the chip flows along the edge of the tool? So everybody, put your hands together. Okay, do it again. Do it again. Do it again. Do it really fast. Thank you. I just thought of that. But no, put your hands together, seriously, and slide one along the other while you're pushing, right? Because there's force. Slide one along the other. So what happens as you slide one hand along the other? So if this hand is the tool, our right hand is the tool, this hand is the chip. As we slide the chip along the tool, what do we know? What's that? I couldn't hear you. It does generate heat. So this is going to get hot in that chip tool interface, because why does it generate heat though? Yeah. Friction. So there's friction happening here. And so we know that there's friction happening there. It has to. Physics tells us there's going to be friction at that tool chip interface, right? Unless we made the tool out of unobtainium with the frictionless coating, right? So there's going to be friction there. There's going to be heat there because of the friction. So some of our energy that goes into cutting is going to waste off in heat. Some of it's going to get wasted as heat, right? So what else do we know about friction? What do we know about friction? You guys all had freshman physics, right? Or high school physics, or you walked on a Worcester sidewalk. What do we know about friction? Yeah. It's a resistant force. How much is the friction force? Do we know how much the friction force is? Yeah. So our friction force equals normal force times coefficient of friction, right? Friction force equals normal force times coefficient of friction. It always does. Whether it's a chip or the bottom of your shoe walking on the sidewalk, friction force always equals normal force. Now, we don't necessarily know what the coefficient of friction is, right? But this is getting us something that we know. What else do we know about the friction? We know one more key thing about friction. We know what direction it is. It's always opposite the direction of motion, right? Friction force is always opposite direction of motion. So there is a friction force from the chip on the tool, from the tool on the chip. You can point it either direction. There's a friction force lined up with that direction of motion pointed this way. But that can't be all the force, right? And there's a normal force. Right? There's a friction force. There has to be a normal force. Let's see, I think we need to draw that this way, right? And what happens if we add those two together? Actually, we do draw it this way. What happens if we add those two together? We get a resultant force. So we take our normal force and our friction force. We've drawn a, let me clean that up. Let's just look at the chip. So there's our chip. We've got a friction force. We've got our normal force. So those are the forces the chip's putting on the tool. Tool's putting on the chip. If we add those together, we get our resultant force. Is there any other force in the system? So the normal force and the friction force equals the cutting force. We use the letter P for the cutting force for some reason. I don't know. People have been using the letter P for 50 years. So that's our resultant force. But if we draw in our workpiece, right, the rest of the tool here, and our workpiece here, what causes the cutting to happen? So we know the cutting force has got to equal this P. We know that this resultant force P has got to be that normal force plus the friction force. And we know the direction of the friction force. So that's cool. But what causes the cutting to happen? Why does cutting happen at all in a machine tool? So what causes the cutting happen? Why does the cutting happen? Somebody at this table. Why does the cutting happen in a machine tool? Yeah.
The torque is being applied either by the object spinning or by the tool spinning.
So we spin the spindle. So we spin the spindle and we move the tool through the workpiece as we spin the spindle. So in this picture, where's the rotation of the spindle? Let's look at it in 3 dimensions. In this picture, where's the rotation of the spindle? It's this way, right? So it's this way. Spindle's working this way. The workpiece is coming down this way. And we're zoomed in on this edge of it. So if we're spinning the spindle this way, the feed just tells us how much material. The feed is just our uncut chip thickness, right? Then this direction of motion, right? Because the workpiece is going this way past the tool. And so this part of the workpiece down here is the bit that's left over, the smaller diameter. So if that is the direction of motion, then this velocity is from the speed, right? It's from the spindle speed. The feed rate is how far, right? Because we're in this orientation here. So the spindle speed is rotating this point around the part. And at this point, what we care about is the vector that represents the straight line speed of that part of the chip, of the workpiece as it goes by. So what's that equal to? What is this V equal to? What are the factors? We call it surface speed. What are the factors that we need to know in order to know the surface speed? There's 2. Yeah? We need to know the spindle speed with what units? We need to know the spindle speed in RPM. And RPM just means rev over minute, right? It's just our way of saying it. Yeah, what else do we need to know? Can we say diameter? Okay. And we need to know diameter. The reason I ask, can we say diameter? Because it's just 2 times the radius, right? We know that the diameter is 2 times the radius. Oh, and the reason I say that is because when we talk about, and this is just so that we do it when we do our jargon or our techno babble or whatever, our speaking, so we speak like other people that are doing machining. And so we talk about diameter, we're talking about the diameter of the workpiece or the diameter of the cutting tool in milling. When we talk about radius, we're typically talking about the radius of the tip of the tool or the radius at the bottom of the end mill in milling. So those end mills, we always draw them like this, right? With sharp corners here and here at the bottom of the end mill. Well, as soon as you start cutting with it, that corner starts to wear out because the sharp points wear out the fastest. We've all seen this. We've experienced it, right? We actually tend to buy end mills that have a ground radius there on purpose because of you guys. They're a little bit harder to break because they don't have that sharp point on the corner that will create a stress riser. And the wear is a little bit more predictable. So because of you guys, we normally just buy them with a radius ground on it. So if I talk about radius, I'm talking about that radius or the radius on the tip of the tool. Sometimes it's the radius on this edge, the cutting edge of the tool, or the radius on the cutting edge of the milling tool. But that when I say radius, that's usually what I mean. Or if we're doing a cutting operation like a pocketing operation, so if that's our workpiece, and then we're cutting out a pocket from the inside with an end mill, these corners need to have a radius because you need to be able to fit the end mill in there. We're going to talk about that later in the class. But if I say radius, I'm either talking about this feature, or the edge radius there, or one of these. That's why I wanted to go with diameter. So the surface speed is going to depend on the spindle speed in RPM and the diameter, either the diameter of the workpiece in turning or the diameter of the end mill in milling. What's the relationship? Let's just cancel the units, right? This is an engineering class. So let's cancel the units. We've got surface speed in revolutions per minute. What's our units for diameter? Inches. And what do we want? Oh, by the way, when we talk about surface speed in either turning or milling, here in America, we use the units feet. So surface speed in feet per minute. We often abbreviate it SFM. I think when you guys are doing programming in Esprit, when you go in to put in the speed, like the feed and the speed part of it, there's SFM. It doesn't even say surface speed, it just says SFM. Yeah, they mean surface feet per minute. In metric units, it's meters per minute. Just to make it so you have to do a unit conversion, right? Because our diameter is inches and our spindle speed is revolutions per minute. We need those to be feet per minute. So what do we have to figure out? This is math, right? You guys know this math. Over here, I heard somebody's got a hand. You need the circumference, right? Because that's the distance per revolution, right? So we need length per revolution. And so let's just get a clean piece of paper. So we've got rev per minute times inches. But how do we take inches and make it be inches per revolution? So how do we take diameter and get circumference? What's the equation? Yeah. Pi times diameter. But we have inches and we need feet. So what do we have to do? Yes. Is it divide or multiply? Okay. Divide by 12. I ask that question seriously because I can never remember if I'm supposed to divide by 12 or multiply by 12. Every single time I do it, I put 12 inches per feet. And this is inches per feet. Okay. The inches divide out, the feet ends up on the top. I get feet per minute. You, if you so choose, could memorize the equations and just know what they are. My brain doesn't work that way. So I memorize the concepts, and then I always figure out the equations. You don't have to do it my way. I used to argue with people about it and say that my way was better. And I suppose that's true as long as you're me. My way is better for me. All right, so surface speed is feet per minute. You need the circumference. Just one last thing. In this operation, if we were facing the front of the part and we got to the center, what's the surface speed? 0. Every single time. If we have a milling operation and we're plunging the tool down, there's flutes at the bottom of the mill, right? You've all seen the bottom of an end mill. There's flutes that go out, cutting edges that go out. We're plunging that tool down. It changes along the flute, right? So all the way to the outside, our diameter is something. When we get to the center, the diameter becomes 0. What's the surface speed at the center of the end mill that's plunging down? 0, just like at the center of the workpiece. No cutting happens when the surface speed is 0, which is why we don't like to plunge end mill straight into the material. We like to move them sideways as they're going down. We'll ramp down, or we'll do a helix down, or even better, drill a hole first and then go down inside the hole and move sideways into the part. So those are things that you want to remember as you're doing your programming and setting up machines. Tomorrow, we're going to connect this friction force. So we've got that friction force, the normal force. What I was trying to get at here was the force that's coming from the torque we apply is pointed in this direction, which is not aligned with the friction force or the normal force. When we have orthogonal coordinate systems, what do? You guys had a math class, right? You can take vectors and you can move from one coordinate system to another. So we're going to talk about the cutting force that's coming from rotating the spindle and the thrust force that's coming to keep the tool from flying away. And those are provided by the machine tool. And we're going to talk about the force that actually causes the material to change shape. So that force that lines up with the plane where we do the cutting. And we're going to see how these all relate together so we can move from one force system to another. So that if we know some information about the cut, we can figure out the rest of it. All right. And this week we will have a quiz. The quiz will cover questions from the stuff we talked about at the beginning of the term. And that's all, really there's no math there other than, I think maybe we talked about profit equals value minus cost over time, right? So did I say quiz? I meant to say homework. I stopped calling them quizzes years ago, except I deploy it as a quiz in Blackboard because it's the easiest way to grade it. But it'll probably be about 20 questions. Some questions talking about this math stuff we're doing. Some of the questions talking about the stuff that we talked about earlier in the term. It's unlimited attempts. Unlimited attempts, open notes, open book, talk to your friends. Just each person submit their own thing. And I guarantee you, if you copy the text of the question, paste it into a Google search bar and click enter, you'll find the method to solve the problem. Half the time it'll be a YouTube video of me explaining how to solve the problem. So please do that. We'll put that out on Friday, and you'll have a week to do that. And then we'll keep up with doing some other stuff like that for the end of the term. But it should be low pressure to do that. And stop sharing. Disconnect. End broadcast.